In this video, you'll learn how the iE650 PLC uses CODESYS MQTT libraries to bridge the gap between your operational technology and IT systems. This tutorial assumes that you already have CODESYS installer set up on your computer. We'll use a demo application developed using the MQTT Client SL library. First, download the IoT Libraries SL package from the CODESYS store. The package includes demo functionality, which allows you to test the library for 30 minutes during development. Once you have the package, open it using CODESYS installer and select the environment you want to work with. In this case, we are using 3.5 SP19 patch 4. From there, the installer wizard will prompt you to continue. We'll use the example project provided with the MQTT Client SL library as our reference. This example is available on the CODESYS website alongside other IoT Libraries SL demos. At the bottom of the page, you'll find the requirements and restrictions as well as the download link for the project. Clicking the download link on the CODESYS website does not download files to your computer. Instead, it opens CODESYS installer, which takes care of the installation for you. From this window, the installer guides you through the process of adding the example projects to your CODESYS environment, similar to how it handled the library installation earlier. When the installation is finished, a new File Explorer window will open, showing the folder where the example files were installed. Additionally, a post-install dialog window allows you to select one of the example projects to open directly. When the project opens, CODESYS may display several dialog windows with suggested actions. Accept the prompts to upgrade the project. Select Yes to update the storage format, and in the Project Environment dialog, click Set All to Newest. This ensures the project is aligned with your current CODESYS version. You may also notice that the message console shows a number of errors or warnings. Each CODESYS version may handle this issue different. In this case, we'll go ahead and update the device object with the corresponding PCM unit according to the PLC. As you can see, the errors in the console disappeared as soon as the device was updated. Next, enter either the PLC's IP address or hostname to establish the connection and log in. This downloads the application to the PLC, after which you can start the program. The main component for this example application is the PRG program that demonstrates the use of the three key function blocks provided by the MQTT Client SL library. If you want to fully understand how each block works, their documentation is available directly from the library manager. There, you'll find detailed descriptions of each function block, including their inputs, outputs, and expected behavior. The example project also includes a visualization object that allows you to easily test both the publish and subscribe functions by defining the input values used by the main program's function blocks. Start by entering the broker connection information and enabling the connection. Once the connection is established, the status indicator will turn green. From here, you can test publishing messages. Select any of the publisher panels, enter a topic, type a message, and press the Publish button. The status indicator will once again confirm whether the operation was successful. The PLC must be on the same network as the broker. For example, a broker deployed on Podman could be used within the iE650, as shown in the demo. Taking the main program and functions from the example project, it's possible to integrate the MQTT client into an existing application. When these objects are copied into a new project, CODESYS may generate console messages related to missing definitions. In this case, you'll need to go to Library Manager and manually add the required libraries as indicated by the console errors. Additionally, the example application does not assign values directly to some of the variables used as inputs in the program. Instead, those values are provided through the visualization object. When reusing the code, these inputs must be explicitly defined, either as constants or as variables within your application. In this demo, the application simulates the behavior of a compression system and a cooling system, both instantiated as global variables. Our goal is to publish their data to an external application. The MQTT client function block is configured as shown here, using inputs such as enable, use TLS, and client ID. The values for these inputs are defined in the var section of the program, allowing full control from the application logic. The next step is to define the payload for the MQTT publish function block. In this case, the payload is structured as a JSON message so that external platforms such as Ignition can consume them. The payload is generated by a custom program and instantiated as a global variable. This variable is then used to replace the default publish message input of the publish block. To trigger the publish operation cyclically, a CODESYS timer from the building automation library is used. The timer is configured with a 200 millisecond interval, which controls how often the message is published. The MQTT subscribe function block remains mostly unchanged from the example project. The main difference is that the subscribe message variable is replaced with a global variable, and an enable input is added to allow runtime control during execution. At this stage, the project is downloaded to the controller and switched to run mode. From that point on, the MQTT client is activated manually by writing a true value to its enable input. Once enabled, the MQTT client function block reports no errors and confirms a successful connection, allowing both the publish and subscribe blocks to operate correctly. The data published by the application can be observed using MQTT Explorer. Here, we can see how the compressor and cooling structures are arranged into a JSON payload, ready to be consumed by external applications such as Ignition. We're publishing this payload using a typical unified namespace structure, where topics are organized to reflect the plant and process context. The payload is published under the line 1 subtopic, representing data originating from that specific work unit. In this example, Ignition sends the data back to the broker, indicated by the presence of the UNSA v1 root topic, which originates from a previously configured Ignition UNS transmitter. In scenarios where this data needs to be retrieved and reused, the MQTT subscribe block is capable of handling this type of topic structure. This block doesn't need an execute rate. Once it's enabled, a constant flow of data arrives from the updated topics. As demonstrated by this custom program, it is possible to store incoming JSON messages from each topic as soon as they are updated. Additional program logic can then be implemented to extract individual values from the JSON payload and use them within the application. This demo illustrates how a CODESYS application can publish and consume structured data over MQTT, enabling seamless integration with higher-level IT and OT systems while keeping the control logic on the PLC.